Good afternoon to everyone. I'm Gabriele Guerrini. I'm an assistant professor in structural engineering at the University of Pavia in Italy, where my research work mainly focuses on the development of tools and solutions for the seismic protection of structures and their contents. Today's talk is the fourth one in this webinar series, and will focus on current and refined assessment methods associated with the nonlinear static analysis of masonry structures following the ERGOCAD 8 provisions. Now, when we talk about nonlinear static analysis, we are concerned about the global building analysis. You are probably familiar with this slide if you've already followed the other webinars of this series. So now we are considering the building as a whole responding to an earthquake with local mechanisms assumed to be blocked, to be prevented by appropriate design solutions. So we consider this global response, and nonlinear static analysis is a tool that can be used for this scope. So let's go quickly through a step-by-step procedure for this type of analysis. You should have already seen something about this first step, which is the numerical modeling phase of the structure. When we consider masonry buildings, we have to model piers, spandrels, diaphragms, and I think in the previous webinar you have seen something about this. You should also have already seen something related to this second step, which is how to carry out the pushover analysis. That is, how to determine the capacity curve of the structure in terms of base shear and displacement of a control node, DC, usually located at the roof, at the nth floor of the structure, and for this reason also identified as D sub n in the ERGOCAD. So once we have performed these two steps, we have our capacity curve, a relationship between the base shear FB or VB and the displacement of this control node, DC or DN. Now we go into the new territory of this webinar series, so to say. And what we have to do next is to transform the capacity curve of the multi-degree of freedom system representing numerically our structure into the so-called capacity spectrum, which is basically a relationship between acceleration and displacement for an equivalent single degree of freedom oscillator, equivalent to the first mode of response of the building in the direction of analysis. After this, we need to transform our capacity spectrum into a bilinear relationship in order to be able to apply the methods to determine the displacement demand for the given hazard, displacement demand acting on the structure. Finally, we need to compare this calculated displacement demand against the displacement capacity associated with specific limit states corresponding to the hazard that we are considering. So today we will focus on these 4 steps, 3 through 6. And let's begin then with the transformation of the capacity curve into the capacity spectrum of our single degree of freedom oscillator. This transformation, as anticipated, is based on the first mode shape phi of the structure. Usually we take the elastic first mode shape in the direction of analysis. And this first mode shape must be normalized in a way that its component at the control node is equal to 1. So phi c or phi n, its equivalent, must be equal to 1 at the control node. Once we do this, so this is done for the model, for the multiple degree of freedom model. Once we determine this first mode shape and we normalize it, then we can calculate two important properties for this equivalent oscillator coming from the first mode, which are the effective mass m star and the transformation or modal participation factor gamma. Here I'm showing you the equations, but you see they're basically related to the mass distribution at the nodes of the multiple degree of freedom structure and to the components of the first mode shape for the same model. Once we have calculated these two parameters, m star and gamma, we are ready to perform our transformation of the capacity curve into the capacity spectrum. That is, we transform the displacement of the control node dn into the displacement of the single degree of freedom oscillator d star by dividing dn with gamma. And we do a similar thing for the base shear FB. We divide it by gamma and by m star, so to find acceleration a star for our equivalent oscillator. And the relationship between a star and d star defines our capacity spectrum. Now, it seems easy. It can actually be easy, but we have to be careful, especially when our structures are 3D systems and we may have some irregularities. In fact, these concepts of transformation from multiple degree of freedom system to single degree of freedom system were defined for planar frames, or in the case of masonry structure, for single wall models. In this case, usually the first mode shape has displacement increasing with the height of the structure. And so typically gamma is greater than or equal to 1. It's equal to 1 if we have a one-story building, because it's already a single degree of freedom system. It can be close to 1 if our multi-story building develops a soft-story mechanism at the first story. And we can also find in literature approximated expressions to estimate gamma. But again, all this can be easily done if we are dealing with a planar frame. When we move into 3D systems, things may become a little bit more complicated to understand. And this is because it becomes important also the space distribution of nodal masses and nodal displacement from the first mode shape. And what happens is that in some cases, we may find that gamma is less than 1. So in this case, it's difficult to understand the meaning of these values. And we need to be careful. Now, this fact that gamma is less than 1 usually happens if we are considering a control node, which is on the wall that is controlling failure of the system, which is an appropriate choice. But under initial conditions, when the building is responding elastically, this wall is not experiencing the largest displacement. This may happen because since the response is nonlinear, a wall that initially is stiffer than another one may get damaged first, and then it may start displacing more. So that's controlling failure, but initially it may not be the most deformable one. So if our control node is on a wall like this, we may end up with gamma less than 1. Now, if this happens and the diaphragms, the floors of our structure are flexible in their plane, then we may move to a single wall analysis. And in this case, we will analyze individual walls as plane frames, plane equivalent frames, and things become again quite easy because we go back to the 2D models for which all these considerations were initially developed. If instead gamma is less than 1, but diaphragms are finite or infinite stiffness, well, in this case, probably we should perform other types of analysis. Dynamic analysis could be a better choice in these particular cases. So let's see a few examples of when these situations may arise. Now, let's start with an easy case, a 2D model. Well, here you can see, I'm showing you the elastic first mode shape and the inelastic deflected shape for the wall highlighted by the blue plane on the left-hand side figure. We can do a single wall analysis in this case because the diaphragms are considered to be flexible. So we extract this wall, we analyze. We see that the first mode shape in the elastic situation and the deflected shape after development of inelasticity are not equal to each other, but quite similar. Displacements are in both cases increasing with height. And in this case, using the elastic gamma factor of 1.32 seems to be appropriate for the analysis. But this is the easy case. As I said, when we move to 3D models, things may not be that straightforward. In this case, we have a stiff diaphragm, or at least a diaphragm with sufficient stiffness to couple the response or parallel walls. Now, in this case, we can see that we have some changes if you look at the plan views, transitioning from the elastic first mode shape to the inelastic deflected shape. We can see that in the elastic first mode shape, displacement concentrate on the right-hand side wall, while in the inelastic deflected shape, basically both walls translate by similar quantities. In this case, from the elastic model analysis, we find gamma of 1.21. Maybe in this case, it would be better to adopt gamma equal to 1 when we look at the inelastic response, because in this case, basically the entire floor is translating by the same amount in the direction of analysis. So it's like a single degree of freedom system. And if our structure, original structure, is already acting as a single degree of freedom system, well, gamma should be taken equal to 1. So in this case, we may want to change the value of gamma from what the elastic analysis tells us to something that comes from observation of the actual deflected shape when the response becomes inelastic. Now let's consider this other example. In this case, diaphragms are quite flexible, so they don't couple really well the response of parallel walls. And in this case, we can see that the elastic first mode shape is completely different from the inelastic one. In the elastic world, basically, the two parallel walls on the right-hand side and left-hand side of the building are moving much less than the inner walls. And here we can really appreciate the deformability of the diaphragm. You can see that displacement concentrate in the center while they are kind of minor on the sides, meaning that our diaphragm is really deflecting like a simply supported beam, for example. When we go inelastic, instead, we can see that the left-hand side wall is getting more damage than the right-hand side wall because of different load transferred to it. And so in this case, the shape, the deflected shape changes completely. Now, in this case, because the diaphragm is quite flexible, we may prefer to avoid this spatial considerations about gamma and just analyze individual walls. You see, we would end up with gamma less than 1, which doesn't make much sense. But since diaphragms, again, are flexible, in this case, just analyze individual walls will probably provide the best estimate of the right solution. Now, next step, after transforming the SDOF structure into a SDOF oscillator, is to approximate the capacity spectrum of the single degree of freedom oscillator. We approximate it with a bilinear relationship. And in this case, we need to be careful again because there is no universal consensus on how to perform this transformation. The ERGOCAD gives some indications, but they don't look really appropriate for masonry buildings. And for this, I would refer you to work by De Jong and Penn from 2017. It's in the reference at the end of the presentation. And they suggest to do what I'm showing you now, which is somehow following the recommendation of the Italian code for masonry buildings. We have to consider two significant points on the actual capacity spectrum, on the curved capacity spectrum. The first point is at 70% of the maximum strength experienced in the curve. So at 70% of A star max. The other point is the one that we record after the peak, after reaching A star max, as we start losing strength, and specifically when we lose 20% of the strength. So when the residual one is 80% of A star max. You see these two red dots on the curve are our two important points. The elastic branch of the bilinear relationship has to pass through 0 and to the 70% A star max point, while we stop our analysis when we lose 20% of the strength. That represents our ultimate displacement capacity, D star U. Now the problem is to determine A star Y, or equivalently B star Y. It's equivalent because they are in the last point of the elastic branch, which has a slope equal to 4 pi square divided by T star square. T star is the elastic period of the single degree of freedom oscillator. Now, to find the yield plateau of the bilinear relationships, to find A star Y or D star Y, we just impose equivalence of the areas below the capacity spectrum, the curved capacity spectrum, and the area below the bilinear relationship. So if we call E star the red shaded area below the curve, then the expression that I'm providing here at the bottom of the slide will allow us to determine D star Y and then A star Y. At this point, once we have our bilinear relationship, we can define a few parameters that are very important for understanding what happens to the displacement demand on our structure. The first parameter is the strength ratio Q sub U. This is nothing but the ratio between the elastic spectral acceleration demand, SE, as a function of T star, of the period associated with the elastic slope of the bilinear relationship, and the yield strength of our bilinear relationship. You see SE of T star divided by A star Y, or equivalent, because we are still in the elastic world, equivalently, we can take the ratio between the elastic displacement demand, D star ET, which is directly related to SE of T star, and the yield displacement. It's exactly the same thing, because again, accelerations and displacement in an elastic structure are directly related, are linearly related. Next parameter is the displacement ductility demand. So this was for the SE T star is for the elastic structure. It's for an elastic demand, but our oscillator is yielding before reaching this point. So as we define a strength ratio, then we will also define a displacement ductility demand. Be careful, because the inelastic demand generally is larger than the elastic demand. You see, D star T, which is the inelastic demand, is generally greater than D star ET, the elastic displacement demand. The ratio between D star T and D star Y, the yield displacement of the bilinear relationship, defines our mi sub Q. Why this subscript Q? Well, because we can define this ductility demand in terms of the given strength ratio. Then we can define also our inelastic displacement ratio. This is the ratio between the inelastic displacement demand and the elastic demand, the ratio of dt star over det star. These three parameters, Q sub U, mi sub Q, and C sub Q, are related to each other by this equation here at the bottom. You can easily see this if you just substitute these definitions within the equation of mi sub Q, and you can find this relationship here. Now, if we perform nonlinear dynamic analysis on inelastic oscillators, we can find interesting results. We can see that our displacement activity demand, mi sub q, is more or less equal to the strength ratio, or equivalently, the inelastic displacement ratio C sub q is about equal to 1.0 for long period systems, when T star usually exceeds 0.35 seconds or so. You can see it from these curves. You see that they tend to values equal or nearly equal to the strength ratio associated with the curves. These curves have been obtained by targeting specific strength ratios for our oscillators. And you can see it also here from the inelastic displacement ratios that they all tend to 1 as the period increases. The problem is for short period structures, for periods usually shorter than 0.35 seconds, because here the ductility demand is greater, becomes quite greater than the strength ratio, or equivalently, C sub q is quite greater than 1. Actually, for periods T star going towards 0, these values tend to infinity. And this is not new. We know this since studies on nonlinear dynamics in the 60s from Newmark and Hall studies. And they defined the so-called equal displacement principle for long period structures, where the inelastic and the elastic displacement demands are pretty much equal to each other. And in this case, basically all methods proposed in the literature to estimate the inelastic displacement demand are good. They're not very sensitive to the period and to the strength ratio, again, because this amplification from elastic to inelastic displacement demand is very small. This C sub q factor is nearly equal to 1. Whatever method we apply in this period range, long period range, you obtain more or less the same result. The problem is for short period structures, where, according to Newmark and Hall, we have the so-called equal energy principle holding. And in this case, as I was saying, the inelastic displacement demand is quite larger than the elastic one. And in this case, however, we have another problem, because this amplification is very, very sensitive to the period of the oscillator, to the strength ratio, and to the hysteretic properties of the inelastic oscillator. And it's here that different methods, unfortunately, may provide different results. Some or less are more accurate, some others are less accurate and may be affected by intrinsic problems. And of course, masonry structures fall within this range, so we need to be very careful. Usually masonry buildings have periods shorter than this somehow, let's call it threshold of 0.35 seconds, and so here we need to be very careful on what we do and on the method that we apply. And so let's look into the methods for calculating this displacement demand. They're basically classified into two main families. But let's look first on how to derive them. We need to consider elastic design spectra, usually given by codes for 5% viscous damping. And of course, it depends on the level of hazard that you are considering to check our limit states. Usually in codes, we find acceleration elastic spectra, SE function of t, but we can easily transform them into displacement spectra. We are in the elastic world, so we can transform spectral accelerations into spectral displacement with a relationship given by 4 pi square over t square. We can also associate for each period the spectral acceleration and the spectral displacement. And in this case, we find what we have here on the right-hand side of the slide, the spectrum in the so-called ADRS format. You see, in this case, we have on the horizontal axis the spectral displacement, on the vertical axis the spectral acceleration. And this makes this spectrum directly comparable with the capacity spectrum of the oscillator, because they're both expressed in terms of A star and D star. SE, the acceleration demand, the spectral acceleration, corresponds to A star. And the spectral displacement, D star ET, correspond to D star. So the two things are now directly comparable. And you see that in this format, in this ADRS format, diagonal lines radiating from the origin of the systems correspond to different periods. So you can identify here TB, TC, and TD, the transitioning periods from the different branches of the spectrum. Actually, the slope of these radiating lines is equal to 4 pi square over t squared, to be exact, but they correspond directly to periods. I was saying we have two main families of methods for calculating displacement demands. The first family is based on equivalent linear system and makes use of overdamped elastic spectra. Basically, we need to define secant periods and equivalent viscous damping. The first method developed in this family was the capacity spectrum method. It was developed in the 70s by Freeman in the United States. It was incorporated in the United States guidelines of the 90s, and then it disappeared there. It's still proposed as an alternative approach in Italy and as a preferred approach in the Netherlands. Then you can find also a revised capacity spectrum method in American guidelines. And to overcome some problems. So with these methods, we have also this optimal stiffness method more recently developed that are again solving some issues with this method. What are these issues? Well, first of all, the capacity spectrum method is iterative, but the problem is that it leads usually to significant overestimation of the demand, especially for short period systems like masonry structures. And this accuracy issues, unfortunately, is intrinsic in the formulation. So with this optimal stiffness methods, which are instead direct, so they don't require iterations, these inaccuracies have been improved for periods down to 0.1 seconds. In any case, we will not go through these methods. They are not mentioned in the ERGOCAD, so we will not go deeply into this. I just wanted to mention you that we have this family of methods. Some of them have more problems when applied to masonry structures, but within the same family, we have improved methods that can be accurately used also for masonry verifications. What we find in the ERGOCAD instead is the N2 method, which belongs to this other family of methods based on the use of inelastic response spectra. In particular, the N2 method was developed by the Slovenian researchers, Fajfar, Vidic, Fischinger, starting from the end of the 80s and then through the 90s. And we find it in the ERGOCAD, and it's also proposed as an alternative method in the Italian code. We find it also in a different formulation, but not so different, in American codes. And also in this case, we have developed some improvements in order to make this method more suitable, more accurate for application to masonry structures. In this case, the method, the N2 method, is already a direct method. It doesn't require any iteration. However, it leads to underestimation of the displacement demand. It's the opposite of the capacity spectrum method. There we had overestimation. Here we have underestimation. However, in this case, the underestimation is usually related simply to the calibration of and the derivation of the equations that are proposed in the code. So to improve this accuracy issues, we just needed to change, revise a little bit these equations, and a conceptual adjustment of the method was not required. Just a calibration of the equations used to predict the displacement, to transform the elastic displacement demand into an inelastic displacement demand. So we will focus on these two methods, the N2 method proposed by the ERGOCAD and the modified N2 method proposed by our research group. In order to discuss and assess the accuracy of these methods and to calibrate the improved method, we made use of a number of nonlinear time history analysis performed on single degree of freedom oscillators representative of masonry structure. So remember that to apply nonlinear time history analysis, you transform the multiple degree of freedom nonlinear structure into an equivalent elastoplastic single degree of freedom system. Well, we have analyzed single degree of freedom oscillators with hysteretic behavior representative of masonry buildings. We basically ended up with 630 target oscillators by changing the elastic period of the bilinear relationship between 0.1 and 0.5 seconds. This is our T star, the elastic period associated with the elastic branch of the bilinear relationship. We targeted 10 different values of A star Y between 0.1 and 0.5 meter per second square. And we consider 7 different equivalent damping ratios between 13% and 20% obtained by combining flexure or shear dominated piers with the mass of the single degree of freedom system. So by combining these different responses in different amounts, giving more or less weight to the flexure dominated or the shear dominated piers, we're able to derive a number, actually 7 different hysteretic responses corresponding to 7 equivalent damping ratios. Then we had to perform our nonlinear dynamic analysis, and to do this we considered 2 different databases. The response spectra for the time histories used for the analysis were interpolated by code like spectra in order to apply the methods, the N2 method and the modified N2 method. And to do this, basically we maintained the PGA coming from the record, and we fit the actual spectrum by changing the code-like spectrum parameters F0, which defines the acceleration plateau, and TC, the corner period, transitioning from constant acceleration to constant velocity branches. Remember that the other transition periods, TB and TD, are all related to these parameters in the ERGOCAD. Now, the first database, database A, included 934 records. The second one, more than 3,500 records. The first one is for tectonic seismicity. The second one was assembled for a specific problem of induced seismicity in the Netherlands. And again, all our oscillators were subjected to all these time history, nonlinear time history analysis. This allowed us to have about 2.8 million of nonlinear time history analysis results to be used for checking the accuracy of the existing N2 method and to calibrate the new N2 method. So how do we apply this N2 method, and what do we find from this checks against the results from the nonlinear time history analysis? Well, first of all, these are the expressions that we need to use for the N2 method. Careful here, I just rewritten them a little bit, starting from the ERGOCAD expressions, so to highlight that in all cases, our target displacement, which is the displacement demand, D star T, is equal to the elastic displacement demand, D star ET of T star. Remember, star identifies the equivalent single degree of freedom, multiplied by the inelastic displacement ratio C sub Q, which depends on the strength ratio. Our elastic displacement demand, D star ET, can be obtained from the elastic pseudospectral acceleration as E of T star by transforming it through this relationship. We multiply the spectral acceleration times T star square over 4 pi square. This gives us the spectral displacement, elastic spectral displacement. And then we may have to amplify it by C sub Q. However, If the strength ratio is less than 1, it means that SE of T star is less than AY star. So we are not even yielding our oscillator. The response is elastic, so C sub Q is equal to 1. We just keep the elastic displacement demand. What happens if Q sub U is greater than 1? Well, the response will be inelastic, and here we have to distinguish between long and short period system. For the N2 method, a long period oscillator is an oscillator that has a T star greater than the corner period, transitioning from the constant acceleration to the constant velocity branches of the spectrum. So if T star is greater than Tc, again, the system is a long period system. There is no amplification of the displacement demand. We can keep the elastic displacement demand, and C sub Q is equal to 1. While if we have a short period system, so if T star is less than Tc, well, only in this case, so for an inelastic system, Q greater than 1, in short period system, T star less than Tc, then we amplify our displacement demand with a factor C sub Q, which is greater than or at least equal to 1, using the equation here at the bottom of the slide. So the first step is to determine the elastic demand. You remember that lines radiating from the origin of the system corresponds to periods. Now, our oscillator has a period T star secant elastic period T star of 0.195 seconds. We intersect the elastic response spectrum at this point. This is our elastic demand. We can see, of course, that the acceleration demand is greater than the acceleration plateau of the bilinear relationship. And so we can define our strength ratio. You see that to move from the elastic demand to the plastic plateau of the bilinear response, we have to multiply the acceleration by 0.33. That is, we have to divide it by a Q factor of 3, basically. And a Q factor of 3 is greater than 1. So, in this case, since T star of 0.195 seconds is less than the corner period of the spectrum, which is at 0.324 seconds, well, we have to apply the amplification, C sub Q, which, if we apply that equation, is going to be equal to 1.44. So you see, then we find our solution, our displacement demand for the inelastic system, D star T, which in this case is equal to 6.24 millimeters. Now, if we do this for all our 630 oscillators using those all those ground motions, and we look at the results, what we can do is to compare the ductility demand from the nonlinear time history analysis on the vertical axis and the ductility demand from the N2 method on the horizontal axis. Ideally, all these points, each point associate the demand from the nonlinear dynamic analysis and the nonlinear static analysis. Ideally, all these points should be on the bisector, meaning that the two values should be the same if the N2 method was perfectly working. Well, of course, it's an approximated evaluation of the displacement demand, but in this case, we can see that we have a problem. You see, this is the median value, and you see that is above the bisector. It means that, on average, the demand from the dynamic nonlinear analysis are greater than the ones predicted by the N2 method. So as I said before, the N2 method is underestimating the inelastic displacement demand. And this underestimation becomes greater as the ductility demand increases. And we can see similar results with both databases of ground motions. So it's not a matter of what ground motions we have used. The two databases are independent. But even if you're using different ground motions, we find more or less the same trend. So this is a problem of the method. Why do we have these problems? Well, there are a few reasons. First of all, is that the relationship between the inelastic displacement ratio, C sub Q, the strength ratio QU, and the period is a very simple relationship, and it comes actually from ductility strength ratio period relationship. Not only, but this ductility strength ratio period relationship actually came from an inversion of the opposite relationship. So the one starting from a given ductility find the possible strength ratio for given period. So all these operations related to the formulation and derivation of the method can affect its accuracy. Not only, the N2 method was calibrated using standard hysteretic rules, typically purely elastoplastic, which can be representative of ductile steel structures, or Takeda hysteretic relationships, which are more appropriate for reinforced concrete structures, but nothing actually representative of masonry systems, which have different shapes for their hysteretic behavior. So this is another factor affecting the accuracy of the method. Then we have another problem, which is not related to this accuracy issue. And this problem is a statement that we find in the ERGOCAD, where we read that the inelastic displacement demand, D star T, needs not to exceed 3 times D star ET. So we don't take it greater than 3 times the elastic demand. But why? There is no reason in limiting the displacement demand. It can be way more than 3 times the elastic displacement demand. So there are several issues in the N2 method as implemented in the ERGOCAD and also in the Italian code. We solved it by developing this modified N2 method. It works pretty much in the same way. The only difference is what to do when the response is inelastic, when the strength ratio is greater than 1. And in this case, we have an expression that can work for any T star. So there is no need to distinguish for short or long period system. When we calibrated the relationship, we chose an equation that could work for both of them. This relationship for T star going to infinity tends to be equal to 1, basically. And we just calibrated the coefficients and the exponents of this relationship so to better match the results from the nonlinear time history analysis on the inelastic single degree of freedom oscillators. Again, it works the same. So we start evaluating the elastic demand for the elastic period of the bilinear relationship associated with the SDOF oscillator, as we did before. We find the Q factor, the strength ratio. Again, in this case, it's going to be equal to about 3. Now there is not even need, as I said, to see if the period T star is greater or smaller than the corner period TC, because we just apply the C sub Q relationship, and in this case, it gives us 1.69. So we multiply this times the elastic displacement demand, and we find D star T equal to 7.3 millimeters. If you remember, before with the standard N2 method, C sub Q was 1.44. You see now 1.69. As expected, is larger because the original method is affected by underestimation of the inelastic displacement demand. So we expect that the more accurate method will provide us a greater value for this amplification. And now, if we do the same comparison in terms of ductility demand from the modified N2 method and from the nonlinear analysis, nonlinear dynamic analysis on the oscillators, we see that the median is very close to the bisector, as we would like to have. Of course, there is still some dispersion in the results. This is because, again, we are using a static analysis. We are starting from elastic spectra and modifying them into inelastic spectra. There are several problems involved in these operations, so the method is not perfect, it's not exact. It's an estimation of the inelastic displacement demand, but we want this estimation to be, on average, to be close to the actual displacement demand from the dynamic nonlinear response of the oscillators. And what we did actually was to calibrate the coefficients using database A, and then check check the method using database B, and we can see that it's quite satisfactory. It's an improvement compared to the original method. The last point is to compare demand and capacity, but this is an easy task because we just transform the demand from the single degree of freedom system oscillator. So we transform D star T into DNT, which is the displacement demand at the control node of the multi-degree of freedom model. How do we do this? Well, we multiply D star T times gamma. Remember, we found the capacity spectrum by dividing the displacements with gamma. Now we multiply the displacement of the single degree of freedom system by gamma, and we go back to the multi-degree of freedom world. And then we just take the pushover curve of our structure, and on this pushover curve we identify limit states associated with the limit states of interest, and we have to check that the demand from the hazard that corresponds to our limit state is less than the capacity. So this is an example. This is the analysis of the botanical garden in Pavia. In this case, the limit state to be considered was a near collapse one associated with an hazard of 975 years of return period. You see the near collapse displacement capacity is here at the 20% drop of the strength, and we have basically 1.8 centimeters or 18 millimeters. The demand, in this case obtained with the standard N2 method, was 15 millimeters, already transformed from single degree of freedom to multiple degree of freedom system. So this is the control node displacement. 15 millimeters is less than 18 millimeters, so the analysis, the building is responding fine, is going to be able to withstand that demand. And we have to repeat this operation for all limit states of interest. Now, with this, I have concluded. Here, I'm providing you some references for the methods, and the codes, the guidelines, papers related to these topics that you may find of interest if you want to go deeply into these methods, these topics. And I thank you for your attention.